Okay, do we have access out? Can we make it out right now?
That's negative. When we came through, the fire was about 50 feet from the road.
The Black Tiger Fire, 44 homes lost. The Butte Fire, 72 fire shelters were deployed. The Mac Lake Fire, 1 fatality. The Paint Fire, 551 homes destroyed. The Dude Fire, 6 firefighters died. Sometimes Mother Nature can cause some very sudden changes in the direction and intensity of a fire. In a very short period of time, a fairly calm fire situation can turn into a life-threatening ordeal. Someday, you as a firefighter might find yourself retreating from an oncoming wall of flame. What you're about to learn can give you some warning signs that might clue you into possible trouble. Warning signs that could save your life. Understanding fire weather is vitally important to you as a firefighter. As our knowledge of fire and fire behavior increases, fire is becoming less and less a wild and mysterious force, and more, a calculated and predictable occurrence. By understanding weather's role in fire behavior, we're taking a giant step towards safe and injury-free firefighting. Weather, as it relates to fire, can be broken down into 3 basic topic areas. There are winds, moisture, which includes relative humidity and fuel moisture, and atmospheric stability. All of the factors and variables that come together to produce our weather can at times seem very complicated. If, however, we break weather down into its basic parts, we find it's built on some very simple concepts. By understanding the fundamental components that make up wind, moisture, and atmospheric stability, you'll start building a foundation of fire weather knowledge that will last throughout your career as wildland firefighters. Obviously, winds have a very pronounced effect on how a fire will behave. Today, we'll discuss 3 different types of wind. Winds that blow on a large scale across the continent, winds that are generated by the buildup of thunderstorms, and winds that are produced on a very small localized scale. But first, let's lay some groundwork. The very thin blue layer of gases that surrounds our Earth is called our atmosphere. This atmosphere is divided into a number of sublayers that are characterized by differences in temperature. The layer closest to the Earth is called the troposphere. It is within this layer that all the constantly changing weather that affects us every day takes place. A very simple principle accounts for most of our weather, that being that hot air rises and cold air sinks. As the air above this campfire is heated, it rises. As it cools, it sinks back down and is pulled in to replace the rising heated air. This cycle sets up what is called a circulation cell. Because the sun heats the equator more than the poles, the Earth produces a similar circulation pattern. As the warm air rises and spreads out at the equator, the rising air creates a void, or a low pressure area. Cooler air from the polar region is pulled in to fill up that void or low pressure area. This forms a completed circulation cell. Sometimes a hot air mass moving up from the equator collides with a cold air mass moving down from the pole. If the conditions are right, eddies are formed off these colliding masses and counterclockwise rotating circulation systems are produced. In the circulation system, air is coiled up through the cell and forced out the top. This counterclockwise rotating air mass is called a low-pressure system, since all the air is being lifted up and out of the cell, producing lower pressure at the ground level. The air that is forced out settles in an adjacent area, forming or adding to a high-pressure system. High pressure because it has more mass and weight. The air rising out of the low-pressure system creates a void that is replaced by the air from the high-pressure system, thus completing the cycle of air movement between the two systems. By placing a device that measures pressure in each system, we would, of course, record lower readings in the low-pressure cell and higher readings in the high. If we connected lines to all those locations across the country with the same readings, a picture of the pressure systems can be produced. There is a constant movement of air between these highs and lows as they try to equal out their pressures. This movement of air is wind. The greater the difference in pressure between high and low, the stronger the wind. The difference is called gradient. Anytime you have hot and cold trying to occupy the same space, expect some unrest. When air masses of different temperatures and moisture content collide, the boundary between the two masses is called a front. A cold front is a cold air mass moving in to replace a warm air mass. A warm front is just the opposite, warm air moving in to replace cold. The first thing we need to look at with the passage of a front is how the winds behave. Generally, in the northern hemisphere, fronts move from the west or northwest to the east or southeast. Wind direction can change up to 180 degrees when a cold front moves through an area, 180 degrees being the opposite direction. To illustrate this, let's look at a fire that is burning under a warm air mass. The winds will generally be out of the southwest. When a cold front moves over this fire, the winds can be gusty and their direction can change abruptly and move from a south wind to a west wind or even as far as a north wind, which is the opposite direction as it was blowing before the front. In both warm and cold front passages, winds are usually strongest before and during the passage. The example I showed was a typical cold front, but fronts can move in from any direction. Typically, on the East Coast, it rains during most frontal passages, but there are times when a dry front moves through, which can cause some real fire behavior problems. Pay particular attention to the fire weather forecast when a front passage is predicted. Winds blow at all levels in the atmosphere. The winds at the higher levels are the ones that drive weather systems across the country. The jet stream, for example. The winds that are produced within a few thousand feet of the Earth's surface are very important. These winds, if they're undisturbed by the topography of the Earth, are called gradient or free air winds. If this gradient wind hits a mountain range that is perpendicular to its direction of flow, an oscillating wave pattern can develop on the lee side of the range. Called standing waves or mountain waves, these oscillating patterns can cause extreme fire behavior. that can create control problems if they reach the ground. This lens-shaped cloud, called an alto-cumulus standing lenticular cloud, is an indicator that strong winds from a mountain wave are blowing above. If you see this cloud, plan a strategy in case the wind should move to the ground and over your fire. Let me illustrate another example of what these gradient winds can do. Let's say that this rock is a mountain range. When a strong high-pressure system builds, say on the east side of the mountains, and a low-pressure system is present over on this side of the mountains, the strong gradient or pressure differential between the two systems will cause the winds to blow over the mountains and down on this side. If these winds are warm and dry, they're called firn or gravity winds. As the winds rush down toward the low pressure area, they're compressed as they move down slope, causing a warming effect. Three things are at work here: strong gradient or pressure differences, gravity, and compression. By the time the winds get to the bottom of the mountain range, their temperature can be as much as 20 degrees warmer. They can be extremely dry and blowing as high as 30 to 50 miles per hour. Mix a fire with these winds and you have a major problem. In Southern California, these winds are the famous Santa Anas. Santa Anas are the most familiar, but this phenomenon occurs all over. In Central and Northern California, these winds are called mono or north winds. In the Pacific Northwest, they're called east winds. And on the east side of the Rockies, they're known as the Chinook winds. Gravity winds also form off the Appalachians. This infrared satellite shot shows the warmer, compressed gravity winds as a darker shade of gray. In the summer of 1990, the Dude Fire in the Tonto National Forest was hit by high winds from a thunderstorm that developed over the fire. This thunderstorm, along with some other factors, caused extreme fire behavior that overran a number of firefighters, 6 of whom lost their lives. Thunderstorms can cause extreme fire behavior. Whenever you see one in the vicinity of a fire, you need to take special notice and understand exactly what might happen and how it can affect you and your safety. Thunderstorms need 3 conditions in order to develop. First is unstable air. Second is moisture.